Okay, as I was saying, I understand that a lot of you are here. The talks after me will largely be looking at metals and acid mine drainage, an issue close to my heart normally. But today I thought I would take my 15 minutes to talk to you about PFAS in mining. I've actually updated my talk after putting it through. So today's talk is actually going to be PFAS in mining. We're in for the long haul. So I just want to start by saying that with a bit of a disclaimer, I put this presentation together to highlight the emerging issues related to the use of PFAS in the mining industry. The pictures that I've included herein are from publicly available sources to provide conceptual support and are not intended to directly represent any specific mining operations where PFAS is or is not known or is suspected or not suspected to be present. And to that end, while I will be drawing on my personal experience, I will not be making any specific reference to any sites because as an emerging issue, it is still quite sensitive for those parties who are aware that they have issues. So I thought, given the potentially diverse range of people that I on board today, that I would start with a little bit of a discussion of what PFAS is, just in case you've heard the word but don't know a lot about it, or maybe haven't even heard it at all. But PFAS, in short, is the term for per and polyfluoroalkyl substances, which are a complex family of man-made fluorinated organic chemicals that have been in them produced since the mid-20th century. To date, they're estimated to include somewhere between 5,000 to 10,000 chemicals, but new chemicals and degradation products are being added to this list all the time. Predominantly, they were originally used in the manufacturing industry in the early years as protective coatings. These are the chemicals known as PFOA. You'll see in the presentation some long words telling you what they are, but the acronyms are usually a lot easier to follow and by far means to say. So I'll just stick to that during this talk. They were also originally used for the development of architectural resins, and these ones are generally categorized as PFNAs or PFHXSs. They make up a significant portion of the market, but where we really see the most environmental issues emerging nationally, globally, is with regards to their PFAS's existence in association with firefighting foams, of which there are many types. So the original firefighting foams largely all comprised of some form or multiple forms of PFAS compounds, and they've been developed since the 1960s. More recently, a group of chemicals known as fluorotelomers has been used since the 2000s as we've attempted to start to phase out the PFAS chemicals. However, we're finding that these fluorotelomers still have similar toxicity risks and still may be of concern, although potentially not quite as severely as the PFAS and other PFAS chemicals of the mid-20th century. The risk to the environment, this suite of chemicals is really highly persistent and bioaccumulative, and it's potentially toxic to humans and ecological receptors. PFAS compounds are forever chemicals. They break down into many, many different subchemicals, but they never entirely disappear. Because they were synthetically manufactured, they're not naturally occurring and really shouldn't be there. One of the more perturbing aspects of PFAS compounds is that they're highly soluble and mobile. They rapidly migrate long distances in a relatively short time into groundwater and surface water. Fun fact is that even polar bears in the Arctic have PFAS in their systems at higher concentrations than many of the other common chemicals of concern from industry. So higher levels than we see TRH or metals. They bioaccumulate quite prolifically. The other thing about PFAS chemicals is the toxicity occurs at very low concentrations. We're talking parts per billion range here, where toxicity impacts to aquatic ecosystems are considered of concern. So basically, at the limits of detection that labs offer these days, it's almost the case of if you can detect it, you can assume that it poses a potential risk. Humans are primarily exposed to PFAS compounds such as PFAS through food consumption and contaminated drinking water. They have long half-lives of approximately 2 to 9 years once we've ingested them. Near aquatic environments, they have a high level of bioaccumulative uptake. Some of the PFAS compounds have longer half-lives in biota in humans than PFAS do. And edible aquatic organisms like fish have been studied and have half-lives that are much shorter than humans, but we do, when we ingest PFAS through aquatic sources, it's generally through our fish consumption. So similar to our awareness around arsenic in shellfish, just your general everyday fish consumption, there's a risk nowadays that we'll be consuming PFAS compounds as part of that. Over the last decade, it's become a rapidly emerging contaminant of concern with a high level of research and investigation happening at a global level. Because health risks are only just emerging, there's still a lot of research being done around it. Some of the risks to human health that we are aware of pertain largely to females and women in pregnancy. So there's quite a few aspects such as developmental effects in infants, lowering fertility in women, increasing blood pressure during pregnancy, and lower infant birth weights that have drawn notable correlations from the studies undertaken. PFAS compounds also interfere with the body's natural hormones and can increase our cholesterol levels. And we've even already noted that they have the potential to affect the immune system. There's already evidence from human and animal studies that PFAS exposure may reduce antibody responses to vaccines like the COVID-19, and that's been in the media of late. It also reduces our infectious disease resistance and potentially increases the risk of some cancer. So with all of these risks to the environment and human health, it's kind of important. I thought we would run through the usual suspects of sources of PFAS in Australia and look a little bit at the geographic distribution of that. So the primary sources that are currently being studied in Australia, our main usual suspects relate to the use of these aqueous firefighting foams or AFFF foams. The key places that we see this occurring are at defense sites, so firefighting training areas as associated with that. Airports, also lots of firefighting response happening there. DFES and fire training facilities, power stations, and fuel refineries in any site with bulk fuel storage, who again maintain high levels of potential fire response equipment on site and do training to undertake that. The secondary sources from those original manufacturing and disposal of consumer products come up at the point of the manufacturing facility. So where Teflon, for example, contains many PFAS compounds, stain resistance on our couches and stuff. Where we actually see that manifest a lot is in our landfills and waste disposal facilities. I work at several of these, and most council class 1 landfills that I've investigated to date have shown it's a low level PFAS plume emanating from them. Water treatment and sewage treatment plants have PFAS components running through them. And more recently, we've identified land application of biosolids that there's quite a large accumulation of PFAS compounds there. And we now may be redistributing PFAS into agricultural environments through the biosolid reuse initiatives. And so these usual suspects, they've been in the media a lot. You guys, largely in Queensland, would be aware you've got class actions around defence sites alleged to have had cataclysmic consequences. Erin Brockovich has been over and highlighted the alarm over PFAS contamination in Queensland. We have class actions being filed by Indigenous communities, such as in Jervis Bay, for cultural loss associated with PFAS. As I said, if it's impacting aquatic ecosystems and biodiversity, and so we see these news articles all the time, and hopefully you've seen them yourself and are aware of this issue, even if you don't really think too hard about it on a day-to-day basis. What we haven't, so as a result of media attention and potential human and biological health risks, PFAS in Australia is under investigation. So there are about 500 sites across Australia that have been identified as potential source areas for PFAS, and they are on a national register of PFAS sites in Australia. That's the map on the left, and it's an interactive map where you can zoom in. That has the manufacturing sites, that has the defense sites, that has the fire training sites. It doesn't have a lot of mining sites, to be honest. Within that, I did a bit of a search of the contaminated sites EPA databases around Australia to see which sites are the high priority sites, those sites that are confirmed and acknowledged as having contamination for which they're moving towards remediation and management. So in Western Australia, there are 28 sites. Queensland has 19 registered sites, New South Wales 43, the Northern Territory 3, South Australia 4, Tasmania 2, and Victoria didn't have a register, but I imagine it would be akin to what we see in New South Wales. These almost exclusively pertain to defense sites, water treatment plants, fire training areas, and bulk fuel storage areas. In Western Australia is the only place that I've found any mining sites registered. We have 2 at the moment. And until recently, mining hasn't really had a mention or really been in the forefront of the PFAS concern. One of the interesting things about the sources that are being investigated is they all have a common point source conceptual site model. So what you will have is a release area, and then you will have overland surface water flow that transports PFAS compounds through sediments and surface water runoff into surface water bodies for uptake by biota and aquatic species, or it also transfers down into the underlying groundwater and migrates and intersects the surface water down gradient. So we have one model's being investigated for the most part, and this is really where the focus has been for the last decade. So I'm not sure how many of you saw the news 2 weeks ago, but just recently, mining and the PFAS issues that are associated with that have crept into the media. So BHP's sensational headline from the West Australian 2 weeks ago, toxic chemical found in groundwater at BHP's NEMI iron ore hub in the Pilbara. So as an environmental contaminated sites practitioner, it's a bit amazing to me how long it's taken for this to hit the media. I've certainly been investigating PFAS in the mining industry for far longer than 2 weeks and probably far longer than the last 2 years. But to date, it's really been kept under wraps. And a lot of mining companies really aren't even have it on their radar as something they need to be concerned about. In Western Australia, PFAS wasn't really identified as a contaminant of concern back in 2006 when our contaminated sites came out and sites got reported on our contaminated sites register. It's just not even in the list of things that many mine sites have been considering. So I want to look at why it's different, where the sources come from, and where we're going in the industry, and why I think that we really are in for the long haul when it comes to managing PFAS in the mining industry. So the primary sources of PFAS in mining are similar to other industries. Obviously, most mine sites, all mine sites have some sort of firefighting management training areas. Unlike defense sites and other areas, mine sites, quite often the firefighting training areas are releases to unsealed ground. You know, what have I seen? You know, flat open ground areas at the top of a mine pit. You know, we don't really work to protect ourselves. And we've been doing this training for over long periods of time, poorly recorded where we do it in many cases. We store a lot of PFAS chemicals in heavy vehicle workshops. And while the use of the most toxic types of AFFF foams is being phased out nationally, many sites still hold large stores of AFFF with nowhere to dispose of it. You know, it's a class 5 material most of the time. There are limited landfills that can take it, limited places to destroy the material. Many mine sites, I have to say, when asked, say that they're still using it because it's easier just to continue to use it and make use of the asset that they have than to bear the cost of disposing it properly. And then the other thing is that all heavy vehicles driving around mine sites, or most of them, contain their own foam canisters. So if you've had a fire response on a heavy vehicle, there have been fire release and spill events, or not spill, but response events where foams have been released to ground. And they could be anywhere, given the network around which haul roads, haul trucks and heavy vehicles travel around a mine site. And that really, the haul truck really is where the difference comes between the point source model that we have for most PFAS source sites and the mining industry, and why this issue is actually geographically much bigger than one would really think to imagine, given probably relatively the smaller volumes of firefighting foams that are contained on mine sites. So we have two main culprits that really do a great job of distributing trace concentrations of PFAS around the environment, the haul truck and the dust suppression truck. And we'll just look at some of those going forward. Hopefully in the background there, you can just see any generic mine site with the broad scale of a haul road network. You've got surface water bodies sitting there, you've got mining operations, and there's a large long transport distances that these vehicles travel. So how do they move this material around? Well, what happens is we get diffuse secondary sources that become a large scale issue, because these heavy vehicles can transport contaminated soils from those point source areas over large areas as they drive around. PFAS impacted surface water runoff will enter sumps and dams. PFAS is impregnating concrete holding bunds and impacts the concrete and then seeps through to the underlying ground. Whereas if those concrete bunds may do a great job for hydrocarbons, the PFAS seeps right through them. We have a huge issue on mine sites with water recycling and reuse, for example, for dust suppression. This can distribute PFAS into process water, water supply dams, recreational areas. So we've been looking at the distribution of PFAS impacted recycled water from dust suppression, and we do find that we will get trace PFAS in the surface soils on haul roads that migrate into sumps, simply from the use of dust suppression water on the haul roads to keep down the dust. One of the shortfalls at the moment is that standard water treatment units are not equipped to process PFAS compounds. So while you think you might be doing the right thing, treating your wastewater, just maybe through your biomax system, an oil water separator system, an AMPRES system, the treated wastewater releases PFAS back into the environment, gets into the groundwater, more overland transfer through surface water, and the cycle recommences and perpetuates. And just to give you an idea, the conceptual site model as a result changes. PFAS is going everywhere. It's transferring via dust suppression. It migrates into recreational water bodies. It migrates into sumps. We pick it up, we move it around, we take it somewhere else. And because it's of a concern at such a trace concentration, everywhere it ends up, it generally becomes a potential risk to either an ecological or a human health receptor. So that, in a nutshell, really summarizes the issue that mine sites are facing. I guess where I really wanted to tie off was really looking at the future risks to the mining industry, because, as I said, it's really just emerging and coming to the forefront. Big companies are only, the bigger mining companies are only just starting to address it themselves proactively. The smaller companies still probably burying their heads in the sand to some degree. So in Western Australia, we're already seeing delays in the approval of mining proposals or extension to existing mining operations emerging. I don't know if they're there in other states or if the other states are to follow, but at the moment in WA, the onus is on proponents to demonstrate that they can provide a clean water supply and that the proponent will not be impacting freshwater potable water sources. We're also seeing delays in water abstraction license renewals or new water abstraction licenses, where the onus again is on the proponent to demonstrate that the groundwater being abstracted does not contain PFAS compounds in it. Mine sites are facing costly contaminated sites investigations to delineate the extent of impacts to soil, sediment, surface water, and groundwater. Quite often groundwater is deep, but because mobility is so pervasive, it's quite easy for PFAS compounds to get into a deep groundwater aquifer. Mine sites are facing the high cost of offsite disposal of large volumes of impacted soils when they do get to the remediation point. We're talking about large travel distances and also the fact that most PFAS compounds have to be disposed of to class 4 or class 5 landfill as a minimum. And then on top of that, mine sites are facing even more costly remediation technologies to eliminate the impacts to their water supply in order to maintain their operations while they haven't treated the soils first. So we see a few mine sites over here scrambling to put in water treatment systems on using newly emerging technologies. And they kind of have a perpetual outlook for operation because they haven't even fully identified the sources or remediated the soil sources in the first instance. So until we can cut that circuit, those water treatment systems will have to operate. Just a bit of a quick ending on emerging water treatment technologies. Obviously, if water treatment is going to be a big thing facing mining, people might be interested in what we do have out there. So there's two main types of treatment technologies that have at least moved out of the experimental stage, and we do see implementation across the country. So there are sorption and separation systems. There's three main ones. MySelects, which is like a binding agent. We have a granular activated carbon or powdered activated carbon sorption system, and ion exchange resins are being used. There's biodegradation being looked at for foam fractionation to hopefully break these compounds down into something a little bit less toxic. All of these still have some of the same limitations as the primary source issues. So most require offsite disposal of the spent media that's absorbing or degrading this material, and that will be to a class 4, class 5 landfill. You know, mine sites aren't generally located quite close to them, so the transport and disposal costs behind that are quite significant. And the other thing that comes in is that these technologies are still sufficiently in their infancy that they can't necessarily cope with other contaminants such as hydrocarbons or nutrients that might also be in the groundwater from other aspects of the mining operations. So they require pre-treatment for other contaminants quite often in order to be successful. So just wrapping back around to my title of my talk, PFAS in mining, we haven't been maybe addressing it to the degree that we should have over the last decade, but I definitely foresee and am experiencing in my own day-to-day practice that it has emerged for the mining industry, and it's going to be here for the long haul while we work out how we're going to manage this large-scale potential issue, given how important it will be to preserve, you know, the operations of our mining resources in Australia. That's all I have today. Thank you.
Thanks for that, Peter. And also thanks to Julie for an excellent talk. It certainly leads into some of the work that I'm going to talk about quite nicely, because certainly since that article came out 2 weeks ago in Western Australia about PFAS, it certainly raised the issue in the mining industry, and you know, I think we'll probably progress to a stage that it's much like PCBs going back, you know, 20, 30 years ago. They were just outright banned, and eventually we got on top of it, but we're not at that stage yet with PFAS, and I think she's right in that we've got a few years before we're going to get on top of it entirely. So just in terms of what I'd like to share today, I'm going to talk about AMD risk block models. We appear to be right at the end. Sorry, I've got my technical assistant here that's going to take us right to the start of the presentation. Apologies for that. There we go, that's better. So talking about the development uses of AMD risk block models. Now, this is a method of identifying, scheduling, and managing mine materials, and it helps to define and quantify the occurrence and distribution and the time of extraction and exposure of each of the materials. It assists us when we're looking at acid and metalliferous drainage, neutral metalliferous drainage, saline drainage, and also helps us work out what the best management options are to either avoid these or eliminate them. Information from block models can be used to develop life and mine material scheduling and dumping for various site infrastructure. and they can be used with other parameters to predict the spatial extent of oxidation of dewatered materials. So the data requirements, what do you actually need to construct an AMD risk block model? Well, it's very similar to an ore resource model, and it's used to calculate material volumes. So you do need calibrated static geochemical data, and it can be quite simple. It can be something like sulfur, or you can use information like net acid generation potential or net acid producing potential. I would suggest that the collection of sulfur and potentially carbon data in most exploration drill core programs is recommended, not just for ore, for waste rock. Some companies do that. We tend to do that, whereas others don't. And it's really valuable information. We can update the model with distribution and volume information over the life of mine. And there's certainly more information out there on block modelling, both in the Australian Government Leading Practice booklet and the Global Acid Rock Drainage Guide. So I'd just like to try and put this into some sort of perspective. This is for a potential mine in Western Australia, and it just really shows the power of being able to have lots of different sources of information and being able to work out what's actually going to occur at the site and what sort of testing you're going to have to do to come up with the characteristics of materials and how they're likely to be managed. So I must stress that this site has never actually been built, but the several learnings from this process that can be used at any potential operation or even an existing operation. So I thought, for the sake of 2 minutes, this really helps visualize why developing a block model for an ore body and waste material is really important. So you can see here that at this particular site, they were going to have to build a new road into the site. It was fairly remote. But we then have sources of information from the exploration drilling program. We've got lots of holes in the ground. Geologists normally have a lot more to work with than humble geochemists. And we have some data. It might be a gold mine, for example, and we know where the high-grade ore is. We can also look at where the pit shell is, and we can define where our waste rock materials are going to come from. And we can get these waste rock materials from drill core and test them well before any sort of mining operation is built. So this is obviously where the open pit is and the waste rock dump at the side there. But the interesting part about this site as we take a flyover is that you'll just catch a glimpse of the tailings storage facility here. And maybe part of the reason that this site didn't get off the ground was that the tailings materials contain 25% pyrite. And my job was to convince the regulators that building such a facility was a good idea. So that was a bit of a struggle. And I think we came to the right outcome in the end, and the regulators came to the right outcome in that it was going to be a very difficult site to manage. And we'll just take a final flyover of the proposed tailings storage facility. So hopefully that gives you a perspective on how we can use information like this to help develop block models and help to understand how materials are going to react depending on their characteristics, and how is there a potential to manage these, or indeed is the characteristics of the materials just too difficult to manage, and in this case it was. There's certainly a whole different range of block modeling software that can be used. You can go from Leapfrog, which is very good but quite expensive, Vulcan mine software, right through to Deswik. Our partners Deswik, we use a lot of their software. But if you want to go to something that's cheap and cheerful, you know, you can have Voxler, for example, that you'll get change out of $1,000 for something like that. And hopefully now I can show you some of the ways that we can use that information. So here's a block model that's already built, and I'll just deconstruct this gradually, and you can see that anything that's red is bad, and anything that's blue is good, and yellow is somewhere in between. So hopefully, if this starts to deconstruct, you can see how the information from the drilling program and the drill holes has been used to develop this block model, and we have the characteristics of the materials. So I thought it was a useful way of showing how to basically have a block model complete and then deconstruct it, and just share how we can use these block models. Now, this one here we had trouble with earlier, but hopefully we'll get it to work. Yeah, so here's another block model, and I believe this is the Voxler one, which is the cheap and cheerful one. It won't give you information that's really detailed, but as a first pass, it can be helpful in building up a block model and identifying areas where you have hot materials and that you're going to have to get samples from and understand both the characteristics and the distribution of these materials. So as I say, it's fairly simple, it's fairly cheap, but it certainly allows you to make a first start before delving into some of the more expensive block modeling software that's out there. This is another one from our partners, Deswick, and it shows a mining operation in the Northern Territory, which I will not disclose the particular site. Hopefully, we're going to get this thing to run. Yeah, hold on a second. Maybe if I, oh, there we go. Well, I think we may struggle getting this to run, but I'll just very quickly run through it. Basically, what you see here is an open pit, and as the material comes out of the open pit, it gets put into a waste rock dump, which is built in such a way that the bad materials, the potential acid forming materials, are stored on the inside of the dump, and the good materials and the final cover materials are put on the outside. So the power of Deswick is that it is mine scheduling and planning software, which allows you on a truck by truck basis to actually work out where materials are coming from, where they're going to, and what the cost of that might be, and what the schedule might be in the mine life. So it's really powerful software for you to allow you to look at different mining options, because mine plans can change on a weekly basis, it has been known. So it does allow you to look at those options, and what we're working with Deswick on at the moment is looking at water quality and how we can use this software and input water quality data to look at whether you can actually meet your environmental authority or license criteria if you change the mine plan, for example. So it's really powerful stuff. It's not on the market yet, but we're working hard at that. This is an overall overview of block models and how they actually fit into the overall life of mine process. So you can see in the top left-hand side there, you've obviously got an exploration drill rig, and you're going to generate some drill core from that. You do want to characterize the materials that are from surface down to the top of the ore body, as well as the ore body itself, and right down to the bottom of the pit, because a lot of these materials from the top until you actually hit some firm rock are actually going to be used as part of your rehabilitation, and quite often they're forgotten about in terms of their physical characteristics. So you know, certainly in Queensland, the regulators are hot onto this with the progressive rehabilitation and closure programs that are getting put forward, and they want to know whether the final landforms are actually stable and can actually be built. So for example, there's no point in putting a sodic material in a drainage structure And if you don't have enough robust material with the correct physical characteristics, you can certainly design something on paper that just can't be built. So that's something that we're working on closely in Queensland, and working with Deswick to show that you can actually build these things economically. So just moving on to the bigger picture, again, working closely with Deswick, we have the integrated planning playbook, where we start at the very beginning and gain some knowledge of the ore body and some of the waste materials. We understand all that and come up with some sort of plan as to how we're going to manage these materials. When we have, a plan or a series of options, we then look at stakeholder engagement and make sure that those stakeholders who are involved, not only the regulators, but site folks as well, and the local community, to make sure that they're involved and they're on board with what's being planned. So then we take it down to a much more detailed planning level. And then we get to the final stage, which is implementation. So there's a whole series of steps that you have to go through, and developing a block model is a key step, but it's only a small step in the overall integrated planning playbook for a mining operation. So finally, some conclusions. AMD risk block models are certainly a useful method for identifying, scheduling and managing materials, part of an integrated mine planning solution. They assist in determining the likelihood of a site having some AMD, NMD or saline drainage issues, and the merits of potential management options. You do require a significant amount of calibrated data. Could be simply total sulfur, or it could be more complex, but generally sulfur can work if it's calibrated. You may want to get carbon data if it's applicable as well. And you certainly want to get that information on waste rock, not just on the ore materials. And you can update the model with distribution and volume information over the life of mine as part of an integrated mine planning solution. And that's certainly, if you go to the Global Acid Rock Drainage Guide, that's one of the key parameters in there that mining operations should be aspiring to, but more often than not, they think that just doing a geochemical assessment up front as part of a feasibility study or an impact statement is fine, and you move on and don't have to do any more. But that's certainly not the case, and why a lot of mining operations have come up with issues as they went through mine life and the mine plan has changed. So thank you very much for your attention, and hand back over to Peter.
Okay. Hi, everyone. Thank you very much for having me here to talk today. And thank you to Pete for inviting me, and to Mark Perlow. So as you just heard, I'm a PhD candidate at UQ. I'm part of a group, a newly formed group actually, led by Dr. Anita Pabaka-Fox, called MyWatch. It's the Mine Waste Transformation Through Characterization group. It's pretty exciting, the work that we're doing, and so I thought I'd share with you a little bit about that, a bit of a promotion for the group, and also to introduce you to my research in this presentation, and maybe give you an idea of the value that it will hopefully add to the common goal that we all share of building a more sustainable and responsible mining industry. But first, Pete actually said to me a couple of days ago, he's like, oh, maybe because you've made the change from exploration geology to environmental geoscience, you might just give a bit of context about that. So I put together this slide. So yes, I was an exploration geologist, and I worked in more of the traditional commodities in gold, copper and silver. I've worked across Australia, Fiji and Indonesia, and I really specialise my skill set in geochemistry, spectral geology and ore body knowledge. But I've decided to make the transition into mine waste management and rehabilitation. And part of the reason for this was I loved my job as an exploration geologist. I really enjoyed it. And I also love the consulting work that I still do as a geochemist, which is a nice little side hustle to being a PhD student. But I guess I really wanted to apply my skill set to an environmental challenge. I wanted to use my geochem my mineralogy and ore body knowledge, as well as my production experience, to be able to approach environmental challenges from a more geology, mining and metallurgy mindset. I still consider myself an exploration geologist, because now I may not be exploring for primary ore deposits, but I am exploring the secondary prospectivity of mine wastes, which, if you ask me, I think is a much more environmentally friendly, ethical and efficient ore body to mine anyway. So with that being said, I'll just move on to the presentation. So as a PhD student, what's really cool is as I'm sure most of you would know, you get to think about things in the macro to micro scale. And so sort of looking at global trends and big picture kind of stuff. And there are a couple of really big challenges that the mining industry is facing, which you all know about because it's the industry that we work in. But what I wanted to talk about, my first challenge was obviously mine waste management. And I guess for me, coming from a production background, it's not really at the forefront of your mind on your day-to-day activities that you're doing. I guess unless you're part of the mine closure planning team, it probably isn't. You focus mainly on safety, how you get the job done most efficiently and how you make money from it. And what you're not thinking about is, I'm going to, from 1 gram of gold extracted from this 1 ton of waste, where that waste is going to go. So I guess the sheer volume of mine waste that we're producing around the world is quite shocking for me. And it continues to shock me every day in everything that I read. But globally, we've got 3,500 active mine waste facilities, and that number can range up to 10,000 facilities, depending on the scale of what you're looking at and who puts their hand up to report the data. But what we do know is that there's over 100 billion tonnes of waste produced every year from the mining industry. If you look at the figure A there, you'll see all the active and inactive mine sites around Australia. There are thousands of them. But a study by a colleague of mine recently published in March this year, studied 286 mines in Australia and calculated 4.3 billion cubic metres of tailings were currently being stored from only a small proportion of all of those mines that you can see in that image. Now, what the really scary thing is that in 5 years, this is predicted to increase to 5.75 billion cubic metres, which is a 30% increase in just 5 years. And this trend is set to continue with global population growth and the increased demand for mineral and energy resources, but also because our ore bodies are becoming more complex, they're deeper, and they're also lower grade, which means that there's more processing that has to happen, more crushing, more fines produced, and more waste material that we have to store. So in Queensland, I've counted that we've got 250 active mine sites, but we also have 15,000 historical mining disturbances. And if you look on figure D there, you'll see the spatial distribution of those disturbances across Queensland. If you expand that out to Australia, it's over 50,000 abandoned mine sites that we've got. So some of these can just be scratchings on the ground from the gold rush time, where people have mined sulfidic material, they've extracted the gold, but they've left the sulfides on surface so that they can oxidize, and it's produced acid mine drainage in the area. But the Queensland government has identified 100 priority abandoned mine sites that they're going to really focus on, that have some quite serious challenges ahead of them in terms of their mine waste management. And these include like Mount Morgan, Mary Kathleen and Mount Oxide. But I guess the biggest point that I wanted to make was that the impact of mine waste, it isn't just a mining company issue, it affects us as individuals right up to the global scale. Figures B and C there are just to remind us of the impact of these. Environmentally, huge footprints, acid and metalliferous drainage that occurs, contaminated air and waterways, habitat and biodiversity destruction. Figure B there is an aluminium waste facility in Brazil, which sits in a very biodiverse environment, and a lot of that land has been taken away for that particular waste facility. And figure C there, as we all remember, the Samarco dam failure in 2015, when 19 people were killed by the dam failure that happened in Brazil. But that figure there is actually from Brumadinho, collapse in 2019 in Minas Gerais, where 270 people died from the collapse of that dam. So I guess the social license to operate from the global community. Power to the people, good on Celeste Barber for that reference. You know, it's really important. It's at the forefront of mining industry, majors, mines, and it really impacts upon their bottom line, which is essentially the economics of the whole system. So mine closure and rehabilitation is super expensive, the maintenance costs, the legacy costs, and yeah, it can really impact upon the way that mines are now managed. We're really holding these companies accountable for their mine waste management. I mean, just for an example, at Mount Morgan, the government is currently paying over $1.4 million per year to operate the water treatment plant for the neutralising capacity of that mine wastewater that's occurring there. So it's very expensive. So the next challenge that I wanted to talk about was critical minerals, and these are going to tie in together. I'm not just chopping and changing, but the Australian government has identified these elements as their critical minerals, and essentially what causes criticality, I guess, is its risk levels. So it tends to have, these elements tend to have limited supply. Their geopolitical environment might not be very secure, and they're used for emerging technologies. So the demand for them is going to significantly increase in the future, generally for electric vehicles, batteries, super alloys, and technologies that we use in electronics. It's become a global trend. Large countries around the world, USA, UK, EU, China, they've all created lists of critical minerals, which tend to vary according to jurisdiction, but tend to be generally the same minerals, elements that we're looking at here. And so what the MyWatch team is essentially doing is we're looking at, well, how can we solve these two major challenges with one solution for the mining industry? And so it's not a new concept, but it has been gaining traction in the last couple of years, and which is really promising, but there's still bottlenecks to this. And so what I wanted to do was break it down really simply and just explain what my PhD is going to be looking at. So if you have a basic mine site and we haul that material to a conventional mill processing plant, you will generally produce your ore and your waste material with all of the issues that are associated with that. So that's your typical conventional mining process chain. But my group is looking at, well, what is a different way of thinking about this mine waste? And what if we look at upgrading that mill, adding a bolt-on, or creating a new milling process and reprocessing process to be able to recover value out of that mine waste? And out of that, we can produce critical metals. We can produce some ore, also construction materials from the gangue mineralogy, can neutralize the acid forming potential of that waste, and try and create a more benign and limited footprint for economic rehabilitation. And we'll be able to fund this all through the value that you extract out of the critical metals and ore that you extract out of that repurposed mine waste. So the link that is really missing here and what my group is focusing on, and my PhD is focusing on, is characterizing that mine waste in terms of its metallurgy, its mineralogy, its geochemistry, and then looking at how we reprocess it and how we extract those minerals to be able to create some economic value from it that can be fed back in to the mining cycle. This research is under an umbrella initiative by the Queensland government. It's called the New Economy Minerals Initiative, or NEMI. It was announced in 2019 and is a 5-year funded project with 2 packages, and we sit under the branch of Old Mines New Value, which is a collaborative effort between SMI and the GSQ. And so the opportunity is to recover critical metals from Queensland mining wastes as part of a global push for waste valorisation. To date, 14 sites have been characterised under NEMI, and under Stream 1, which Dr. Laura Jackson has been leading up to determine the new economy metal contents in these waste streams. So we've got a really awesome group of researchers working on these projects. They're led, as I said, by Dr. Anita Pabaka-Fox, and we're looking at transforming Queensland's mine waste into green ore deposits. The project aims are to look at mine waste sites across Queensland and identify economic deposits of new economy metals, particularly the critical metals, to define the relationship between ore body geology and mineralisation style and the cycling of these metals in the surface environment, to identify new drill core analysis technologies for defining these contents in the waste zone, and to develop novel mineral processing options for green recovery of new economy metals. And how we're doing this is with a team that's got geochemists, mineralogists, experts in mineral processing. We've got microbiologists and PhD students, which is very exciting. How we're doing this is through 3 streams. So the first stream is a first pass investigation of mine waste, where 24 mine sites will be looked at in terms of, well, do they actually have economic value from critical metals? Second stream is the detailed site investigations, which is where my PhD comes in. And the third are bespoke mineral processing methodologies. So my case study is on Capricorn copper, which is the old gunpowder site. This is a really cool site because it's got several different waste streams, and it's also had a long history of mining in it. So we're dealing with historical waste plus current waste that's being produced on the mine. Cap Copper is a sedimentary hosted copper, silver, cobalt deposit. The copper mineralization actually sits with a cobalt rich pyrite, which is very exciting because then that sits in your tailings. And we're currently focusing on the Esperanza tailings dam, which has a much higher pyrite content and cobalt content in it. So the research themes that I'm going to be looking at in my PhD are tailings characterization through the mineralogy and geochemistry. I'm looking at cobalt tenor and deportment, cobalt mobility, the character of it and where it sits within the mined material through to the milling material, and what occurs to it during the processing, and then what happens to cobalt in the tailings. Cobalt cycling in the near surface environment. Obviously, you will have sulfidic material that will host cobalt, but you'll also have oxidized material in the upper portions and also on your waste rocks. And this will be able to be processed differently. So we're looking at metallurgical methods for cobalt recovery, waste valorization options for additional critical metals. And this will all eventually feed into like an economic risk framework to look at economic rehabilitation for this particular site, but also for other sites in Queensland. And we'll use a variety of techniques that are drawn from geology, environmental and metallurgy to be able to characterize these waste materials. So I guess the takeaway from my research is that it's a collaborative effort between the Department of Resources and the Sustainable Minerals Institute. And it's really a feasibility study for economic rehabilitation in Queensland. The Queensland government's asking, is this somewhere where we want to put our money? And is this a viable mining option for the state? We want to build renewed interest in Queensland resources sector, looking at green ore bodies. It's a framework for operating and historical sites, and also the application of circular economy principles to mine site rehabilitation. So watch this space. Thank you very much, and very exciting mine waste materials. So yay. Thank you.
Thanks, Loren. Thanks very much for that. I'd just like to remind everyone, if they've got some questions, please get them in. We do have at least one from the floor, and I'll kick that off as well. And this one's for you, Julie. And I've got an addition to it because I think we came up with the same question, more or less. This is from Asdisa. What are the permeability characteristics of PFAS? What material could stop or reduce the transmission of PFAS through, or what material could be used as an impermeable liner to control its mitigation, or its migration, I should say? And can I add to that, along the same lines, are there options, I guess, for on-site disposal rather than removing a lot of this material off-site?
Okay, so I don't know if permeability is the correct question for that, but it's very soluble. So what we quite often see is that beyond source sites, like in sumps, for example, we will find it in the source water or the sump water, but we won't necessarily see it sticking to the sediments. It remobilizes quite frequently and will migrate down through the surface profile to the groundwater without leaving. They might leave some very small fractions there, but quite often if it's only there in small quantities, you'll just find the underlying groundwater impacted with very little transport residue left from the PFAS compounds. So, you know, the obvious solutions for reducing mobility are things like HDPE, which can be used as an impermeable barrier to contain PFAS, but this isn't always suitable in terms of hydraulic flows of water and cost feasibility to mining operations. Other things like activated carbon-based products, for instance, like there's one out there called Rembind Aqua Gate that allows water to flow through it, becomes like a passive remediation measure. However, hydrocarbons and PFAS quite often come together, and hydrocarbons in water and soil can affect the absorption capacity of the carbon, which always has to be considered as well. So that's the first half of the question, I think. I think your second half there, Peter, I need you to repeat, sorry.
Yeah, no, just in terms of, are there options for disposal of, say, the contaminated soils on site? Yeah, can we make lined dumps and things like that, or is it still a case of having to ship them off site?
Well, possibly, but for most people that would be a licensable activity, so it's not out of the ballpark. But you wouldn't just be able to say take it to your waste, you know, your class 1 waste dump. You may be able to put a containment cell in there, but again, a clay liner or a concrete liner would be insufficient for containing it. Possibly if you've added a product like the Rembind and stuff that's binding it up, we may get there. We haven't really seen many examples of that yet. I know defense sites are looking at that themselves as their own remediation methods. Obviously, they have lots of material that is impacted and it's not all going to our landfills, but those technologies are still caught in the process.
Okay, thanks, Julie. Question for Alan and the block models and AMD in general. It's probably less of an issue now in Australia because we don't have too many outcropping ore bodies anymore. But where we do have around the world outcropping ore bodies that are reasonably sulfidic, how do you model that, given that the country rock that you're starting with and everything around it is possibly already acid generating? And how do you then deal with that material?
Well, I guess if it's there naturally, then yeah, you're going to have to. Whether you have to do something about it or not is another matter, because it's really Crown land and it's government's issue. But if it's part of a mining operation, then yeah, you're still going to have to probably drill it out and understand what you're dealing with. You know, it's a difficult situation in that if it's natural. Like many years ago, I worked at Copper Mines of Tasmania, and you know, that's a historical operation that's been there over 100 years, and they actually had to have an act of parliament, the Copper Mines of Tasmania Agreement Act, to allow an operator to come to site and be only responsible for the impacts of any activities that they you know, had compared to historical activities that the previous owner had. So yeah, I guess it really comes down to two things. You know, who's responsible for it, and the second thing is you know, understanding what you're dealing with.
Okay, thanks, Mark. Alton, sorry. A question for Loren from Mark Perlow. Any plans to make a block model of the tailings or waste rock facility at Capricorn Copper?
Thanks, Mark. And I was really interested in Alan's talk because of the work that he was doing for looking at, you know, PAF forming material in block model form, which is really, really cool. So that would be a nice thing to add to my PhD. But yes, in terms of making a block model for cobalt in mine tailings, I mean, it is. It's part of what I am interested in doing. I think site will probably manage that aspect of it. They're really keen to do some sampling and to be able to understand the value that sits in their tailings facility. I mean, the facility is 45 meters deep, the one that I'm looking at, the tailings stand that I'm looking at. So they've got quite a bit of material that they would be able to get some value out of. So yes, it is on the on the plan, and I will have some input into that.
Thanks, Loren. I've got another question, and I think we're getting pretty already much outside our welcome, but I'll get this one in anyway. And I guess it's a combination of Julie and Loren. Where you have PFAS and other materials which are, as you mentioned, Julie, highly easily distributed through the water table and highly mobile, and you have those materials in your tailings dams or waste rock material where you're perhaps, Loren, looking for extracting critical minerals, is it both an opportunity to remediate both those things and get benefit two ways, or is one going to potentially impact on the other, or the ability to do the other? Julia, I might let you go first on that one.
That's an interesting question. There's been a lot of focus in the research around the coexistence of PFAS and hydrocarbons and their difficulties in interacting and remediation. There's been a much lesser focus of interest, I think, because we haven't been focusing on it in the mining industry between the associations and limitations on metalliferous impacts and PFAS. To be fair, I haven't seen anyone directly investigating their tailings dams yet for PFAS. That still may be in the to come basket. I mean, certainly there's always opportunity for everything, whether it's 2-phase or 3-phase, but I think we're probably a long ways away from having a remediation solution behind that.
Thanks, Julie. And Loren, I guess it is early in your research, but have you come across anything that would potentially prevent getting things out of waste rock and out of tailings, or is it just something that we throw a bit more money at and solve it?
Look, I think with mine waste material, you have many different deleterious elements in there, and different organic material that's a problem as well. And so the concept of reprocessing it and working through it again would be to make the end product as benign as we possibly could. So it would have to be a multi-faceted approach. It's not just to extract one particular element out and then leave the rest in there so that it's a continual problem. We've also, like at Capricorn Copper, I mean, I haven't heard of PFAS at Cap Copper, but at Capricorn Copper, for example, we've got, other elements that could be potentially dangerous in the environment, and so we would look at extracting them as well and minimizing the waste deleterious nature of it when we put the waste into a more sustainable remediation process. So yeah, I mean, it's not just a one plan for one element. It would certainly be an approach that would look at the whole waste material and all of the different elements in it, and try and remove most of those negative effects.
Excellent. Thanks, Loren. Well, we are over time, and I don't want to overstay our welcome, so I'd take the opportunity on behalf of the AIG to thank Loren, Alan and Julie for their time, and also thank Mark Perlow for helping put this together. So thank you all.